In this next video, we will be walking through the code to implement reinforcement learning for the game tic-tac-toe. We will go through it at a high level, looking at the key classes and methods that makes it all come together. Then we will show you how it works, how to tweak some of the configurations, what impact that has to the end result, print out some of the key variables like the value table to show you what it looks like so you can get a better intuition for how it all comes together. We have linked to the repository that contains all of this code in the description below. We're first going to a bit of an overview on the key functional blocks in the code. This will make it easier for you to understand once we actually get into the code. You'll see some functions related to initializing states. What the code does is to loop through the entire state space of tic-tac-toe and creates a dictionary that has the key as the hash value of the state. And then the value of the dictionary is a tuple, which has two elements. The first element is the actual numpy array, which encapsulates the data of the state. And then the second element is an boolean, which indicates whether it's the end of a game, in which case it would be true or false. This is just an illustration of what I was talking about. So what these two functions will do is to loop through all of the possible states that you might see yourself in a tic-tac-toe game, and it will save it inside this variable. As you can see, it's a dictionary, meaning it's a key value pair. And the key is a unique hash of the state of the game. And the value is a tuple with two elements, the actual state of the game, and a Boolean true false indicating whether it is the end of a game or not. In this implementation, the all states dictionary has around 5,478 rows. And you might actually have heard of the tic-tac-toe game as having fewer states. And it's because our implementation here is not that smart, and it does not recognize the rotational and reflection symmetry of the different states as being the same state but rotated. That's why there are so many states. And when you look at this particular function, you'll see that it's a recursion. And so it will take you from initialization, where all the 9 spaces are empty, to the first player taking the first spot, and then the second player taking the second spot, third player taking the third spot, fourth player taking the fourth spot, and so on until the game terminates either in someone winning or all the spaces are already taken and it's a draw. And when they reach the end of a game, they will backtrack up the tree and then go down the different branches until all of the states have been mapped out. And you'll see that the policy for both player 1 and player 2 is very simple. It'll just take the first available slot according to the sequencing. It doesn't really matter because they're not really playing the game. They're just trying to map out the entire state space. So you'll see that in the code, there's a states class. Every state that the player passes through will have a corresponding state object. And inside this state object, it has a number of different methods. You can convert the 3x3 numpy state array into the corresponding hash value. You can check to see if the state is an end state or not. It also has a method where if you give it an action, for example, row 2, column 0, and the symbol, it will place that symbol into the state and return the next state object as if that action had been taken. And here we've got some illustrations. So you'll see that this is the state class, and each state has a number of internal variables. And this is the hash method, which basically takes the 3x3 numpy array and turns it into a hash value. So it takes this and gives you back this. And this would be a unique number associated with every state. And on this side, you'll see a isEnd method. And we don't have to go through here, but it's basically checking like, oh, are there any symbols where we would have 3 in a row, or is the entire, are all the 9 slots filled? And so it will determine whether it's true or false in terms of whether the state is an end state, and whether the winner is the player 1, is the other player, or whether it was a draw. There's also this next state method where if you pass in the state and you pass in the I and j, which defines the action that has been chosen, and the symbol. So you'll see here, this is the 3x3 numpy array of the current state. And let's say you decide, I want to take an action where I is 0. So this is the row. This is a column reference. So it's this one. They want to take this one and put a symbol X there. I want to put X here. What this method does is to take all of this and return a new state object where the symbol has been placed at the corresponding spot. Okay. Now, there's a set of variables and methods that's associated with the player. And you'll see later on when we initialize a game, actually we have 2 instances of this player object playing against each other. And in this class, you can define the learning behavior of the player by setting its epsilon value, which indicates how greedy it is during training time, and also the step size, which affects how quickly it learns from the multiple games that it plays during training. It also has a number of methods. So it can update its own value table by backing up the states after it receives a reward at the end of a game. We'll see this in more visual ways in a second. It also has a method to choose an available action that maximizes the value, or if it's epsilon-greedy behavior, occasionally it will select the action at random. And finally, there's a method that saves the value table after training into a policy binary file. So it's in permanent storage and can be retrieved the next time the player wants to play and wants to bring its best self to the game. You'll see here, it will, from this backing up, it will keep saving onto this value table. So let's have a look at the player class. In the initialization, you'll see that there are some variables that when you instantiate a player, you can define the step size and the epsilon value. And then it's got some internal variables, such as a list of states that the player has gone through in this particular game, and corresponding to each of those steps, whether it was a greedy action or not a greedy action, and also what symbol it's using for that particular game. And you'll also see here that every time the player moves into a new state of the game, it is appended to the state list. So for every game, the player knows exactly its sequence of states that it has passed through, and also corresponding to those steps, whether the action was greedy or not. And this is useful when it comes to updating the value table in the backup procedure. This part sets the symbol for the player, and then depending on which symbol is the winner, it will get assigned the right type of reward. So if the player symbol equals to the winner's symbol, that means the player won. So it gets a reward of 1. If it's a draw, then it gets 0.5. And if it lost, then it would get a reward of 0. Now this is how the value table is updated. The value table in this code is referred to as estimations, and each player has got its own estimations variable. And the variable is another dictionary. There's a hash key corresponding to a value, which is a number, which is the estimated value of being in that state. And at the beginning, the value in every state will be 0. But as you play more games, you will find, let's say the player went through all of these states and then ended up winning. And so it didn't get any rewards along the way, because the way this has been implemented only gives reward after you win or lose or draw. So here you got a reward of 1. And so you sum up all the rewards that you've received along this path and then give this state a value of corresponding to that sum. And then you backtrack along all of the states you saw in the game and calculate what's called a temporal difference and discount it by the step size to calculate the updated value for this state. You keep going, and every time you do this, you write the new value into this dictionary. This is the method within the player class that enables it to choose the right actions. You'll see that in this initial part, what it's doing is taking the state of the game as it stands and seeing what are the remaining spots that haven't been taken yet. It's creating a list of all available actions based on the current state. So in this particular example, it loops through and it will find that there are 3 available actions. There's this, you can take this one, you can take this one, or you can take this one. And this is how we define the actions with the I and the J. So this is like 0, 1, 2, the second row, and then the zeroth column, which is this one. And then after you take that action and put the symbol in, then this will map onto a hash value, which shows the next state if you took that as an action. After creating these next state hash values, it can then go and look up the estimations table to get the latest estimate for the value and see which one of these steps results in the next state that has the highest value. And if the agent is being greedy, then it will always take the highest value and choose that action and pass that action back into the game as saying, this is the action I want to take because I've actually looked ahead 1 step already and saw that the resulting state of that action results in the highest value. However, because this has a epsilon-greedy policy, depending on what the epsilon value is, occasionally it will take a step where it selects the action at random. That's because during training, you know that your estimations table does not have perfect values for these estimates because it's still learning. It started off with 0. And so you want to occasionally try something new to see if that results in a winning game or a better path, and then you can learn from those experiences and keep updating those values. But what's important here is that if it was a random step, you don't want to update that value because you know that it will be suboptimal for that particular step. All right, so let's look at this last one. It's called the judger class. So what the judger does is to pull players together and initialize a sequence of games. It assigns the symbols to each of them. It keeps track of whose turn it is. It declares the winners, and it resets the players. And it has a method inside where you don't have to redeclare this every time you start a new game. You only need to redeclare it every time you initialize a set of players and an environment. And if you want to play a lot of games, you just need to invoke the method called play inside judger. Right, so you'll also see a function called train. What train does is to initialize the two players and sets their settings. And normally, if you're in training mode, your epsilon value is somewhat greater than 0, like maybe 0.1. And it also initializes the judger. It will loop through the play for X games. And it's also referred to in the code as epoch. So for example, during training, you want these two players to play 1,000 games, then you would have a epoch of 1,000. And so you will keep looping through, invoking the judger play method 1,000 times. And every time the game finishes, the player will do a backup to update this value table. So this value table over the 1,000 games will become better and better and more accurate. And at the end of the training, so after you complete the 1,000 games and the value table has become really well populated, it will then save this into a binary file called policy. And finally, there's another function in there called compete. So after you've trained, you might want to use what you've learned to play a game. And in this case, it will initialize the players, set epsilon to 0, because you don't want to do any exploration while you're competing. You just want to take the knowledge that you've learned from your training and do the best you can and do a greedy play against a real opponent. Each player will actually load their policy from the binary file, which they saved into at the end of the training. And they'll loop through the play. For example, it might play 100 games, and it'll keep track of the winning and losing stats to see ultimately who was the winner and who was the loser. All right, so we're going to go through a demo of the code in this next part. I'm using a code repository on GitHub that I've linked to down in the descriptions below, and this is an amazing resource covering all of the examples in the book. And right now we're going through the one in chapter 1 called a tic-tac-toe.py. So that's the file I have open here. All right, so if you scroll to the bottom, let's just use it and see what it does. Then we can go and dive into the detail of the actual code. We have 3 key functions. The first one is a training function. What we would normally do is to train the players such that they will store their learning into these binary files. The first player has its policy stored here. Second player has a policy stored here. And when they go into compete mode, they will compete with each other using a greedy policy. So just following these 2 policies without doing any exploration. This number here is just the number of games they will play under each of these regimes. At the beginning, before any training, their policies would be empty. So let's just run this and see what happens. So you'll see that through the different epochs, it will print out the cumulative win rate of player 1, player 2, and the draw rate. And you can see here at the beginning, in the first 500 games, win rate of player 1 was a little bit above player 2 because player 1 always goes first. And as they get better and better, the win rate decreases towards 0 and the draw rate increases. And we'll never get down to 100% draw rate during training because firstly, in the first few hundred epochs, you're doing a lot of essentially random moves because your policy is not that refined. And these rates are cumulative. And secondly, there's an element of epsilon-greedy that ensures that there's some degree of randomness in the moves depending on the actual value of epsilon. So for that reason, these will never be, all 0 or all 100. But you can see here as we entered into the compete mode, where we played 1,000 games of player 1 against player 2 using the policy that they learned through training, draw was 100%, and neither of them won any games. And that's because the game mechanics of tic-tac-toe is such that if both players play perfectly, the game will always draw. So let's try something else. If we go into the compete function, which you'll see here, you'll see that both players are following a greedy policy, meaning epsilon is 0. There's a 0% probability that it will take a random move. But let's say if we set this to 0.5 for player 2, save it and see what happens. So it will not affect the training. Player 2 is still accumulating the best policy it can because this epsilon is only affecting the compete policy, not the train. So if we scroll up, train for both players is 0.01. Okay. But if we go into the results of the competition, you'll see that player 1 now wins most of the games and player 2 only wins some, and the draw rate is much lower. And it's because player 2 is not playing perfectly, because for 50% of the time it is following an epsilon greedy policy, meaning 50% of the moves are completely drawn at random. Let's scroll up and have a look at this. So here's the initial definition of the configuration of the board, which is 3 rows and 3 columns. And then this is the state class, which we have discussed previously. We've got a number of variables within this class. The self.data is a numpy array, 3x3 array, and this is where the actual state data is stored. This is the hash function. So this is the hash function. I won't go into details as to how this works, but essentially it takes the numpy 3x3 numpy array and turns it into a unique number, which is then used as the key in the dictionary for identifying and retrieving that state. Is_n is basically a bunch of logic that tests whether there's a row of 3 symbols in a row, or if all of the 9 spaces are filled. And if either of those conditions are true, then is_end will be returned as true. Otherwise, it's false. Next state basically takes the current state of the board and then the proposed action, which is defined as the row and the column of the space that you want to take, and that's the symbol that you want to put there. And what it does is it makes a copy of the current state and then adds this move onto it and then returns a new state object. And then this is just printing out of the state if we want to see what that looks like. The next 2 functions is run every time this file is run. And what it does is it creates a dictionary called all states, and it uses a tree search method to loop through all the possible states that the tic-tac-toe game can possibly be in, create a hash of each of those states, use that as the key of all states, and then the value is a tuple consisting of elements of the current state and then the is_end associated with that state. And you can see this calls a subfunction, and this function is a recursive function that just goes and loops through all the possible states. And in this tree search, both of the players are following a policy, as I mentioned before, of just taking the next available slot. Okay. Now you'll see the judger class. So every time we want to start a game between two players, this class is instantiated. And in the initialization, you'll define the players, you'll give them the symbols, and you will initialize the state object. And then it has some methods here for resetting the players, for taking turns between the two players. And then this is the play method. So once you've determined that these two players with these configurations are going to play against each other, if you want to play 1,000 games, you don't have to reinitialize the judger object. You can just invoke the play method to play each game. So you can see here the players take turn taking actions, and then it gets the next state, and then it keeps looping through here until a winner is declared or the game is finished. This is the player class, and for each player, they have their own value table, and it's called estimations. It's a dictionary, and the dictionary is essentially, the key is the hash of the state, and then the value is a number representing the estimated value that a player can hope to get moving forwards if they find themselves in that current state. And then this is a step size, which determines how quickly the value estimations update with the new games and new data that's being brought in from each episode. Epsilon defines how much they explore versus exploit. And then you've got two internal variables here. You've got states, which is a list, and this keeps track for each game, all the states the player passes through. And correspondingly, you have a list indicating whether each of those states were as a result of a greedy move or a non-greedy move. And this is important because if the state resulted from a non-greedy move, then you don't want to update the value of that state when you do the backup. And this is, at the end of each game, these two lists are reset. Every time someone makes a move, the state is appended to the states list variable, and by default, the boolean true is appended to the greedy list. And then setting the symbol. So you can set the symbol for each of the players, and so it will know if the winner equals to my own symbol, then it means I won the game and I get 1 point. If the winner is 0, then it means it was a draw, so I get half a point, and otherwise it means the other person won, which means I get 0 points. And backup, this is a very key method under each player. They will loop through all the states that they've been in for that game in reverse, and then calculate the TD error. So the new value estimated is stored in the value table called estimations under the hash of that state. The TD error is added to the existing value, multiplied or discounted by the step size. You'll see an extra thing here called multiplied by self-greedy. So what this does is essentially set TD error to 0 if greedy is false, meaning this will become 0, and so there's no update. This is another really important method. It is the acting method. So you'll see here that the code loops through the current state, sees where there are empty spots, and accumulates this next position and next states list that stores all of the possible actions you can take from now on based on what spaces are still empty. And then it will draw a random number, and if that random number is less than epsilon, then it will just draw randomly from that list of available actions. In the greedy list to false. So when you come to doing this backup, it will essentially turn TD error to 0, causing no update. However, if it's above epsilon, then it will take this approach, which essentially is looking up using the hash, the latest value estimations from the value table, creating a list of it, shuffling it, and then sorting it in reverse order. So the action or the next state that results in the biggest value is at the front. And the reason why they need to shuffle it is because if there are two different actions that results in the next state of the same value, then you want to be able to draw from them randomly. So this just creates a randomness if the values are equal. It will take the first action after that sorted list, and it will then return the proposed action that this player should take. And you'll see here there's a method that will save the estimations dictionary to permanent storage, which is a file called policy first or policy second. When it's in compete mode, you'll see that it will load this policy back into memory and follow that in a greedy way to play the game. And I didn't really explain it here, but this code just has a separate class called a human player. So just in case you want to play with player 1 as opposed to having player 1 play with player 2. But I won't go into this in any detail. Here's the training mode. In training mode, you define how many epochs or how many games you want to train the players over. This is just how often it prints out the results. And you initialize player 1 and player 2, and here they're set with the same level of epsilon, meaning they both explore and exploit in an equal way. Here you instantiate the judger class and pass to it player 1 and player 2. And these are just for statistical tracking, tracking the win rate of player 1, player 2, and how many times it draws. And now it's going to loop through all the games that you want it to play during training. And so it will invoke the judger object play method. And then it will keep track of who won in each game so we can see the win rate of each of the players. And you can see that at the end of each game, both players are asked to do a backup. So of those 1,000 games, after each of those games, it will back up, update the values of all the states that it's traveled through for that particular game, and keep track of it in their own player memory. And then at the end of each game, the judger object will reset and then play the next game. But in reset, the estimations or the value table is not reset. It accumulates. That's the whole point of having a training function that will loop over 1,000. It means you're learning over 1,000 plays and accumulating that knowledge inside the value table called estimates. And after it's all done, at the end of the training function, both of these players will save their policy to these permanent files. And so when you move on to competing, you can compete over 10 turns, 100 turns, and then you can set each of the players to have epsilon. And normally you would want them to be following greedy play protocol because you're competing. You shouldn't be exploring while you're competing. But if we do this, that means both players are playing perfect games, meaning every game is going to be a draw. So the rest of this is quite similar to the training, but you'll see here, it's loading the policy in and it's following the policy that it learned as opposed to learning the policy, which was what the training function did. And yeah, the rest of this is pretty similar. So there we go. And let's see. These two functions at the bottom are ones that I added myself so I can print out the policy just so I can have a look at what it looks like. So let me just comment out these two and uncomment this one. So you might be curious, like what exactly is in here and what does the value table look like? So here we're just going to print out the first 10 rows of the player one estimations dictionary. So you'll see here, let's go up. So what's in the first row is a hash value for this particular state. So this state is like all zeros. And then the estimated value that one can hope to obtain if you're starting from this state. And that makes sense, around 0.5. So all of these are 0.5. Let's see if we can find a higher one. Oh, here. So state 7, which has a hash value of this, is estimated to give us a value of 1. And that's because, and in this case, player 1 has been assigned the star value. This is a winning state for player 1. So that's it.